Evening, everyone. Welcome to our discussion of relativity. Got an interesting topic for you tonight. Can't take all the credit, of course. You can see the author of the theory. We're going to talk all about Albert Einstein and what kind of things he found and learned about. Try to give you a little taste of what the theory is all about. I want to start out with a simple question. Why are we talking about this theory of relativity? And I think the answer begins, as you see here, with the fact that humans have always tried to understand this incredible universe that we live in. It's just in our nature to be curious. We wonder what we see up in the night sky and here and on the earth. While ancient cultures had some ideas, we really kind of look back towards the ancient Greek civilization as the first one to begin exploring our universe with a scientific approach. I won't go into the details, of course, but you know that science originates with observations of the natural world. We come up with ideas that might explain it, and then we test those ideas to see if they're correct or not. And this gradually, steadily leads us to a better, improved, enlarged understanding of the universe. So even though the Greeks were wrong on some things, they really, again, originated that approach that has allowed us to learn so much, as we're going to learn about tonight in our lecture. You go down some centuries through time and you come to the Middle Ages. There were several notable scientists, especially in the field of astronomy, that took the lead. People like Copernicus, Johannes Kepler, you see over on the right there, Galileo. These men made tremendous steps forward in helping us understand our place in the universe. And towards the end of the 1600s, of course, Isaac Newton wrote his monumental work, the Principia. This has often been regarded as perhaps one of the greatest science books of all time. Newton here established the laws of nature that are so familiar to us today. And we generally think of his picture, his model, as kind of a mechanistic universe. In other words, he pictured the universe as this very complex, almost like a clockwork type of mechanism. And the familiar laws, again, that we're familiar with today, he established laws of motion, law of gravity, those kind of things that we see in everyday life. Now, Newton's theory worked quite well for several centuries, and really, it still works quite well in everyday life. But our topic tonight, of course, as you can see, is to talk more about Einstein's theory. And we call this a relativistic theory, or relativistic universe, because as you're going to see, the principle of relativity is really its foundation. Now, many of the things we're going to learn about are not going to be obvious to us in everyday life. They may only be observable with difficulty, but they have led to a better, deeper, broader understanding of the universe. And as you're going to see, they allow us to explain so much more that we cannot explain without it. Some of these things may feel a little bit odd, a little counterintuitive. I always tell my students, you just got to give yourself a little time, and they'll begin to feel more comfortable. So, how did Einstein come up with the theory? We'll take a few minutes to talk about that. We're going to start by looking at a couple of different mysteries that scientists of the 19th century uncovered and could not explain. Frankly, by the mid-19th century, scientists were feeling pretty comfortable, pretty confident that we had developed Newton's theory and understood the universe pretty well, but little did they know how much more there was to learn. So let's go ahead and look at a couple of different mysteries, and I'm going to talk through these so that you can obviously follow where this goes. Number one, during the late 18th century, two scientists named Michelson and Morley did an experiment. They wanted to see if the speed of light would change if it was measured with and without the motion of the Earth. At the time, there was understood to be this universal, what was called the ether at that time, that they felt was kind of an absolute reference frame. They wanted to test that idea. So what they did was they used a device called an interferometer. And basically, as you see on the right here, it took a beam of light and it split it into two perpendicular directions. One direction going with the Earth's motion and one direction perpendicular to that without the Earth's motion. And the idea was to measure the speed of light in both directions. And they expected to see that there should be a difference. In other words, in one direction with the Earth's motion Well, we're used to, of course, adding motions together, aren't we? If you're maybe, I don't know, traveling on a bus or something and it's going 40 miles an hour and you take a baseball and you throw it down the aisle 20 miles an hour, someone on the sidewalk is going to see that ball moving at 20 plus 40 is 60 miles an hour. We add velocities in everyday life, don't we? And that's what they were testing here. Could we add the Earth's velocity to that of light? Well, notice the result. There was no difference. This was astonishing to the scientists at that time. It basically told them that there was no universal reference ether, as I mentioned. And this caused them to stop and pause and say, well, we got to rethink this. Something as simple as motion, at least as far as light was concerned. So this later on proved to be something that Einstein thought a lot about. Why is it that everyone sees light travel at the same speed? Remember that. We're going to come back to it in just a minute. There were several other things. I'm going to just focus on one more, and let me talk through this briefly now. If any of you have any familiarity with electricity or magnetism, this may be familiar. If you take a magnet and it's at rest, it has a magnetic field. If, however, you take that magnet and you move it through some loops of wire, interestingly, the magnet will cause an electric field to form. Okay, we say that it's induced or generated. Well, when scientists did a simple experiment, they found something very unusual that Einstein commented on. This is his words. He said, seen from a moving magnet. In other words, if you were at rest relative to the magnet, there would be no electric field. In other words, if you are not moving relative to the magnet, there's no electric field. But he said, seen from a state of rest, in other words, where the magnet is moving through the wires, there is a magnetic field present. You see the point? He said the existence of the electric field is a relative one according to the state of motion. Now, this isn't some trick of nature. He said the fields have an objective reality, but note it is apart from the state of motion of the observer. So in other words, the observer's motion determines what you see. Again, this was not something that Isaac Newton's theory could explain, nor could the scientists of the day. So this sometimes happens in science. When we have a reasonably good theory, sometimes we make observations, and we realize that the theory doesn't quite explain them. Now, we may not have to completely discard the theory. It may just need some updating or something. In fact, as I mentioned, Isaac Newton's theory is still very useful today in everyday life. We can still use his laws of motion, his law of gravity, those kind of things. It's not that it was completely wrong as much as it was incomplete. So here's where Einstein now comes into play right about the turn of the 20th century, and he begins thinking about those things. In particular, example you see here, and again, the notion of the speed of light being the same to any observer, regardless of their motion. So that kind of gives you a little taste of where this came from. There were several different things occurring that scientists wanted to explain better. Okay, so let's now dive in, take a few minutes, describe the two main parts of the theory of relativity. The first is called the special theory, which Einstein published in 1905. This deals with constant motion. In other words, no change in speed, no change in direction. Okay, he kind of limited the theory, and that's why it's called the special theory. It's a special case, so to speak. The first fundamental concept is that motion is not absolute, but relative. In other words, there is no universal reference frame that we can measure everything against. You must measure something relative to something else. Okay, I'm going to give you a quick example here. Look to the upper right. Imagine we're floating out in space, far from the Earth. We look down. We see an airplane flying from Africa to South America. Now, this airplane I've selected to fly at exactly 1,670 kilometers per hour. Why? That's about 1,000 miles an hour. And that's the speed that the Earth is rotating at the equator. Okay, now, to you and me floating up in space, we look down and we see that airplane flying, but To someone on the ground, of course, they're going to look up and see it flying overhead at a very high velocity, right? To someone in the airplane, they're going to look down at the ground and see the ground moving at a very high velocity. But to you and me, the airplane is motionless. That exact speed is counteracting Earth's rotation. So to you and me, it stays fixed while the Earth rotates beneath it. Do you see the point that we are in what we might call a reference frame, or frame of reference is another way to say it, different from the people on the Earth? What is the difference? Well, obviously, the people on the Earth are moving relative to you and me, floating out in space. So this is what we mean by relative motion. It seems fairly simple and straightforward, and it is, but we're going to see some interesting consequences of this concept of relative motion. We must always remember that we must specify what we are measuring our motion relative to. Okay, now let's go back to our second point. We touched on it just a little bit, how the speed of light is the same to all observers. Now, a minute ago, I mentioned that we are used to adding velocities. Again, if you're traveling, I don't know, in a car, an airplane, a bus, and again, you have some motion inside of that, we add those motions, don't we? But that's not what the theory of relativity says. Look at my diagram here in the lower right. I'm going to introduce you to our cute little round spacecraft here. We're going to be flying this around a little bit. And there you are. I'm going to put you in there upside down. You don't care. It's out in space. And notice you're going to go ahead and shine out the front there a flashlight. Now, to you, of course, the light is moving at the speed of light, right? But if you were flying from left to right at a pretty high velocity, and someone else was down on the ground looking up at you, again, you see this light traveling at a certain speed. We might normally think that we must take the speed of the light and add the speed of your spaceship for this observer. But that's simply not the case. The observer will always measure the speed of light the same as you. Now, how can that be? That sounds almost, incomprehensible. It's just everyday experience that we add velocities. Well, we're going to get back in just a minute to explain a little bit more about that. But this is basically what the theory is telling us, that the speed of light is the same for all observers in all reference frames. Okay, so hold on to that thought. We'll come back in a moment and address that. How can that possibly be? The third thing that the special theory of relativity is famous for, as you see here, is this well-known equation. E equals mc squared. It's really telling us that energy equals matter or mass multiplied by the speed of light, which is c. Okay, now of course, c is a pretty high number. The speed of light's pretty fast, so if you square that number, it's a pretty big number, isn't it? So as we're going to see in a minute, this equation allows us to explain things we cannot otherwise explain. The special theory also talks about two other effects. Maybe you've heard of them. They sound a little mysterious, kind of interesting. Time slows down. How can that be? Time feels so universal to us, doesn't it? We don't even think about it. There's just time. Well, Einstein said that time is not necessarily a constant. Let me try to give you a little taste of that with this diagram in the upper right. You can see our little round spaceship, and we're going to invite our new friend Jackie to come and help us with her little spaceship. So in the top, you can see that you in your ship are moving from right to left at a very high speed. Why? Because this is where these effects become noticeable. We'll see in a minute that they're not really noticeable at low speeds in everyday life. But let's say you're moving from right to left at a very high speed, 70% of the speed of light. Jackie's sitting in her little round spaceship. You and her have agreed you're going to perform a special little experiment. She's going to take a light beam and she's going to send a pulse of light up to the top of her ship and back down. It's going to bounce off a couple of mirrors. And she's going to measure how long it takes for that light to travel. And we're just going to use some arbitrary units here, okay? You can see she measures it at, let's call that 10 microseconds, okay? We'll just pick a number here. But remember what we just said a minute ago. Motion is relative. In other words, it is equally valid for you to say, I'm not moving. Jackie is moving relative to me at 70% of the speed of light. Note what happens. Look closely. I know it's a little bit hard to see in my picture there. But if you're sitting still and Jackie's moving and she shines that pulse of light upward, during the time the light is traveling up and back down and then back to her ship moves a little bit to the right, doesn't it? Can you see that? It's kind of hard to see. I probably should have picked a little clearer picture. The light beam travels more on a triangular type of trajectory. It's not just straight up and down because her ship has a component of motion to the right. Now, we've said already several times, the speed of light is always constant. And if the speed of light is always constant and the light beam has a longer distance to travel, it must take a longer time. Can you see the difference there? So in other words, later on, if you and her were to meet for a cup of coffee or something, and you say, oh, so, how'd the experiment go? Oh, good, I measured 10 microseconds. You would say, well, that's not what I measured. I measured maybe 15 microseconds. So who's right? Well, you both are. How can we say that? You both are in a different reference frame. You both measure time differently. Now, this is not some trick of nature. This would really occur if we could devise such an experiment. The point being, we must begin to let go, relinquish this concept that there is one universal time. That's simply not the case. Time does flow differently for different observers in different frames of reference. So that's a very interesting and yet sometimes a little bit difficult thing to grasp and kind of internalize. How about this next bullet? Object mass increases. What does that mean? We think of any object as a certain amount of mass. Well, according to Einstein's equation, if you look down there, energy equals mass. So there is a form of energy. Many of you may be familiar with this. That's known as kinetic energy. That's the energy of motion. When a body is in a certain motion, a certain velocity, it has a certain kinetic energy. Well, Einstein's telling us that the more energy it has, the more kinetic energy, the faster it's going. That's equivalent to additional mass that the body has. Now, if the body has additional mass and we try to speed it up, slow it down, we accelerate it, we generally do is we would apply a force to it, but the force produces less acceleration on a moving object than on a motionless object. And this has been verified, as we'll see a little bit later. So it is true. The body's mass increases. Now, again, in everyday life, we're not going to notice these effects. Look at our graph down in the lower right here for mass increase. You see the red line there. As you move from left to right, there's your speed in percentage of the speed of light, 20, 40, 60, 80%. And notice even if you get up to almost 40% of the speed of light, there's not much change at all. But notice after that, after 50, 60, 70% of the speed of light, there is a significant increase. As we're going to find out, no object can reach the speed of light. This is one reason why. Because as the object were to go faster and faster and faster and faster, its mass would increase. And notice how sharply the curve goes upward at the end there. Mathematically, if a body were to approach the speed of light, its mass would increase to infinity. Now, of course, that's not possible. There's no such thing as infinite mass, is there? So here's where Einstein also, again, was able to say, so therefore, no object can ever reach the speed of light. Its mass would increase too much. So these are really the effects, so to speak, of motion at very high velocity near the speed of light, as we've just seen. Well, the theory also mentioned a couple other strange things. Number 3, length contraction. Look at our little spaceship in the upper right now. We look over, Jackie's moving by us at high velocity. The spaceship looks kind of strange, doesn't it? Looks kind of compressed in the direction of motion. What's going on here? Well, Jackie would measure her ship just fine. She's inside of it. She is not moving relative to the ship, is she? But as she flew past you at high velocity, if you had a way to measure carefully, you'd measure that the length of the ship from left to right there is shorter. How can that be? Well, how do you know the length? You have to measure it. And notice how I've put this. The measurement of 2 points occurs at different times. You can't measure two things simultaneously. There must be some finite or non-zero amount of time between measurements. So during the measurement, one part of the ship, one side, one measurement point is going to move relative to the first one. Do you see that? So this would be something that, again, is not going to harm Jackie in any way or her ship, but that's what you would measure. And how about simultaneity of events? What does that mean? Two observers moving at different speeds would measure when events occur differently. Let me talk through this for a minute. One more time, we've got our two little ships. We've deliberately taken Jackie's ship and kind of stretched it out. It's not going to look like that. What we're trying to show is that her ship is moving from left to right now. Okay. In this experiment, you and her have agreed that as she flies by you, just at that precise moment, somehow she'll be able to push a button and one light will light up at the left side and the right side of her ship. Okay? Call it a red and a green light if you like. Okay, so as she flies by, she pushes that button. And if she does this just right, of course, the light from the red and green light, left and right, let's call it, they're going to travel towards you, those light waves, and they're going to reach you simultaneously at the same time. You say, oh, that's nice. She hit the button. I see the two lights lit up at the same moment. Well, what's Jackie going to see? She is moving at a high enough velocity that as she pushes that button, those light waves take some finite or non-zero amount of time. They're not traveling instantaneously. They are traveling towards you. She, meanwhile, during that time, is moving to the right. Can you see that she's going to close that distance? She's going to close the distance to the light waves that are traveling from the right side of her ship. And since it's a shorter distance, she's going to see those light waves first. Meanwhile, the light waves from the left side of her ship have a longer way to travel to catch up to her. And she's going to see that light flash later. Okay, so once again, you meet for another cup of coffee and say, oh, that was interesting. I saw you push the button, the lights flash. And she said, well, that was really weird because I saw the other light go off first than that one. This is not a trick of nature. This would really happen. She would observe the light differently. So in other words, the two of you would disagree on when the lights blinked. Now, these are the type of experiments, Einstein called them thought experiments, that he developed. I'm certainly not going to take the credit for them. And you can see they're simple, yet they're very powerful in helping us understand what's going on here. I mentioned already in the special theory, E equals mc squared. I'll go ahead and tell you, many of you know that this equation explains why and how the sun makes energy. The sun is converting mass into energy. And by the way, that's also how our nuclear weapons work. But the point is, without that equation, without this theory, we could not explain how the sun shines. So you can see, obviously, why that's important. Okay, so I hope that gives you a little taste of the theory, but you can see my question down there. People sometimes say, come on, really? Does all this strange stuff really happen? This doesn't sound right. Well, it's a fair question. And you know, the answer, of course, in science is we want proof. We want evidence. So let's talk about how we test special relativity. First of all, time dilation. Look to the upper right. You see a little diagram here. I've made a few notes. We get on Earth cosmic rays from space entering our atmosphere at very high velocity. And these change into a particle called a muon. And those muons can be moving at almost the speed of light. So what that means is they definitely are going to feel the effects of relativity. Now, you notice it says they have a half-life of about 2.2 microseconds. That's a very short time. Given that number, after 2.2 microseconds, half of them should change into another particle. And then after another 2.2, another half and another half. By the time amount of time goes by, most all of them will have changed. And as it says, less than 1% of them should reach the ground. But that's not what we find. At that high velocity, the theory tells us the half-life of the muons grows approximately 10 times longer. The particles literally, you could say, live longer before they decay. And as a result, we measure approximately 25% of them reaching the ground. Isn't that interesting? So there's a natural phenomena that we need relativity to explain. In the bottom, you see a picture of two gentlemen aboard an aircraft back in 1971. They took some very, very state-of-the-art atomic clocks, our most accurate clocks, and they basically flew around the world with them on a jet aircraft. Now, a jet aircraft doesn't really go all that fast, but it goes fast enough that these atomic clocks did measure a difference in the amount of time that elapsed compared to other stationary clocks on the ground. You can see they lost 59 nanoseconds going eastward, 273 nanoseconds going westward. That's partly because of the Earth's rotation, but the point is they measured a difference in time using those clocks compared to the ground. Years ago, the astronauts who went to the moon loved to joke that by traveling so fast, they lived a few microseconds longer than the rest of us. Okay? So different velocities experience different time. Later on, I want to mention this more than once, our GPS systems that we love to use. We pull out our phone, type in an address, we want to see where we're going. They must compensate for this effect. Why? Well, these GPS systems rely on satellites in orbit moving at a high velocity. That velocity must be taken into account because these systems measure very, very precise location here on Earth. If it were not for the correction from the theory of relativity, your GPS system would not work. You'd be off by miles. The calculations would simply not work. And I've already mentioned again, E equals mc squared. That equation explains how the sun makes energy. Simple as that. So these are just a few of the many tests that have been performed on special relativity over the years. Every single time the theory has passed the test. Well, now let's move on to general relativity. This was considerably more effort for Einstein to come up with, develop, and write. He actually required some help from other scientists. Why? Because it deals with accelerated motion. He found this to be more challenging for us to understand. You can see he also began with a concept here. We think of space and time as two very different things. Einstein said they are intimately connected together. They are inseparable, and they are not absolute. We've already kind of seen a first taste of that, haven't we? That time is not absolute. Well, neither is space. You'll see what we mean by this. Let's talk about some of the effects. Number one, matter curves space-time. Let me show you what I mean. You look over to this right-hand diagram, and what we're showing here is a little white object with a certain mass. We could call that the Earth, for example. Notice our blue framework is showing what we might call uniform space. You know that if you were to draw this cube, nice straight line, you see it's nice and uniform, but notice how near the object the lines are distorted. Einstein says this is curved space-time. And interestingly, it's not just space that's curved, it's time. If you want to use a different word than curved, you could say it's distorted or some other word, but we generally talk about how space-time is curved. What's interesting about this is that matter curves space-time, but curved space-time causes matter to move differently. It causes an acceleration. In fact, we could go so far as to say that the effects of gravity and acceleration are equivalent. What does that mean? It means that the curvature of space-time is what you and I perceive as gravity. Now, we're very used to thinking of gravity as this mysterious force. And did you know that even Isaac Newton wasn't 100% comfortable with some mysterious force, some invisible force? He's like, where does it come from? What causes it? We still can't say what makes the force, except to say, well, matter makes it. We can't say how. But Einstein very nicely kind of eliminates the question. He says, we don't have to think about forces. We could just think that matter curves space-time. You'll see a few examples of this as we move on, okay? The final part here, one of the primary effects, is it says that time slows down in a gravitational field. So really, this is a second type of time dilation. We saw a minute ago, time slows down when an object moves at a high velocity. But here we have time slowing down because of the effects of gravity. So let's explore each of these a little bit more. Okay, let me show you, by the way, what this would look like if our Earth were put into motion. Imagine the sun at the center, of course, and the Earth's going to orbit around it. But I'm going to click that. I thought that was a great little animation. They're actually pretty hard to find. I was able to locate this one, as you can see, on a website. And it nicely shows, greatly exaggerated, of course, what we envision. Many times when we're teaching relativity, we'll use a two-dimensional flat surface. Picture in your mind, perhaps a rubber sheet is kind of what we like to use sometimes. You take a rubber sheet, you set a bowling ball on it, you know what's going to happen. It's going to bend that sheet, that's going to distort it. That's a two-dimensional illustration, and it's very useful. But I thought it might be nice for once to see a three-dimensional demonstration of curved space-time. To me, at least, it makes it a lot more clear that this curvature is in 3 dimensions. It's not just in 2 dimensions. Okay? So let's talk about how we know general relativity is true. Number one, something we call frame dragging. I haven't mentioned this yet. Einstein said that mass, for example, picture the sun, very massive object, is going to curve space-time. It's going to tend to have a slight dragging effect with space-time as the sun rotates. So what does that do? Well, you can see there in the upper left and upper right, here we have an animation of Mercury, and we've greatly exaggerated. As it orbits around the sun, Mercury's got a little bit of an elliptical orbit. It's going to get closer and further. Notice how the long axis of the orbit is slowly drifting. And on the left, you can see a composite image of that. So we call that precession. It's a very small effect, but no one could explain this in the 19th century. They had measured it by, I believe, the year 1853, and no one could explain this. They kept imagining even that maybe there was a new planet near the sun that was causing this. There's not. But Einstein explained it using general relativity. In fact, some years back, scientists here on Earth launched several satellites into Earth orbit. Now, Earth is less massive than the sun, but it's massive enough that we precisely measured this effect around Earth. The satellite's orbits slowly but steadily precessed or shifted over time. How about this second time dilation I mentioned? Think of it as due to a difference in gravity. In other words, notice in my picture on the left, if you put a clock at the top of a mountain, it's farther from the center of the Earth, isn't it? Put another clock down at sea level, it's closer to the center of the Earth. Those clocks are going to feel very slightly different forces of gravity, and they're going to measure time differently. This has been confirmed several times, as you can see there. Okay, our two scientists on the right are a little confused because one clock's higher than the other, and they're not telling the same time. It's not quite that simple, is it? But you get the point. The farther you are from a gravitational field versus the closer you are, time will flow differently. Time will slow down in a stronger gravitational field. Okay, so we'll see a very extreme example of that here in just a minute. Maybe some of you know what I'm getting at. Okay, so these are the effects of general relativity. These are two very simple tests, but there's more. And basically, we could talk then about gravitational lensing. Let me explain the principle, then we'll come back in a minute and see some examples of it, okay? We said a minute ago that any massive object, take the sun, is going to curve space-time. Let's imagine we're looking down from above at the sun's north pole, and the Earth, of course, is orbiting around it. In the distance, there's a star, and let's just say that the star is pretty much lined up with the sun. okay, from our perspective? Well, as the light from the star comes towards the sun, it's going to experience that curvature of space, and the path of the light is going to curve. It's going to get bent, so to speak. Once it clears the sun, it will once again travel in a straight line towards Earth. But what do we see? We see the apparent position of the star shifted from where it actually should be. Again, not a trick of nature, not a mirage of it. This is what actually happens, as you're going to see in a minute. I'll show you an example of that, okay? This was first seen, as it says, back in 1919 during a solar eclipse. Today, we see this effect commonly. When we go out and explore other galaxies and other galaxy clusters, we must use general relativity to explain what we're seeing, curvature of space-time. So it's very evident, very important in astronomy. You've probably heard of gravitational waves. Here's a simple example of how these can be made. It's just a simulation, but generally these are most detectable with two massive objects orbiting each other. Okay, and it turns out, of course, that as they orbit each other, they're making these waves of gravity. Well, that energy has to come from somewhere, doesn't it? Where does it come from? It comes from the orbital motion of the objects. In other words, over time, these objects are going to have to lose a little bit of their orbital motion. And that means they're going to gradually, slowly get closer. They're going to spiral closer and closer. Now, it's a very slow effect, but over time it speeds up. And as they get closer and closer, the rate at which they do so increases. You can probably guess where that's going to end up. So we'll come back to that in just a minute as well. Now, I've done another whole lecture on this topic. I am going to talk about it here in this context, but probably some of you have heard of the LIGO, Laser Interferometer Gravitational Observatory. Scientists have proposed a even better one. The LISA Observatory would be a space-based such a facility. These are our ways of detecting these. I won't go into great detail exactly how we do that. Some of you know that these facilities have two very long arms, and they can measure distances extremely precisely, smaller than the size of an atom. And if by chance a wave of gravity passes through these two long arms of this facility, scientists can detect the difference. They will see one arm grow slightly longer, one slightly shorter. They'll know that a gravitational wave has passed through the facility. Okay. Well, I wanted to also take some time, of course, meaning that I not only teach astronomy, but I think many of you are interested in astronomy, to talk about relativity in astronomy. Here's everyone's favorite topic, black holes. I have another whole lecture on black holes. I'd like to go see that on YouTube. So what's a black hole? Well, simply put, it's an object where the escape velocity is greater than the speed of light. In other words, the gravity is so strong of this particular object, it's so dense that nothing can escape. Another way to say that would be to say that the curvature of space-time is so great, so extreme, that nothing can escape. Now you can see from our animation here, there is also gravitational lensing. The gravity is so strong, it's causing the light to move around it in a very complex way, isn't it? In fact, I've always found it interesting that in these animations, we literally are seeing light from the back side of the black hole. Isn't that interesting? The light is curved and bent so much, we literally are looking behind the black hole. So that's pretty crazy, isn't it? Now, remember earlier, Einstein told us it's not only space that's curved, it's time. And what we mean by that in this context is that time, again, in the vicinity of such powerful, strong gravity, is going to slow down dramatically. In fact, technically speaking, at the surface of our black hole, time would stop. Now that's a pretty crazy thought, isn't it? Time would stop there. If we were to watch something falling towards the black hole, it would appear to take longer and longer and longer to get to the black hole. So here's a prime example. In astronomy, where we must use general relativity to explain what we're seeing and for us to be able to learn about black holes, to understand them, to investigate them. They're still to this day a very cutting edge type of a topic. Astronomers continue to work to understand them. Let's go back now to that topic of gravitational lensing. I mentioned that this was first detected in 1919. Now remember, this was only 4 short years after Einstein published his theory. Okay, the idea is this: if you look down at the bottom picture at the top, you notice a field of stars, and astronomers, of course, could take pictures of stars all they want. But you probably also know that in just the right circumstances, right place, and the right time, we get solar eclipses. The moon blocks the sun's light. So the advantage here, of course, would be that if the sun were in a certain area of the sky, we don't normally get to see the stars near it, it's just too bright, but not during an eclipse. During a solar eclipse, when the moon blocks the sun, the sky gets dark. Maybe some of you got to experience the eclipse back in 2017. You can see stars near the sun. So here was a prime opportunity for astronomers to measure the positions of stars during a solar eclipse and compare that to their positions without the sun in the vicinity. In fact, this was the very first major test of general relativity. Einstein predicted this, and he basically challenged the world's astronomers to go see it. And so sure enough, one of the most prestigious, well-known British astronomers of the day took it up, took the challenge, went to a remote location that was in the prime position, and took that photograph. You see there's some stars, you can't see them very well, they're marked with little tick marks. What do you think he found? He found exactly what Albert Einstein predicted. He found those stars shifted by almost exactly the same amount that the theory predicted. And again, you see that in the upper diagram there, how we're just using an example of a star having a slightly different position. This experiment is really what brought Einstein to worldwide attention. Sure, the scientists had known of his theory, but this was an astonishing thing, proving and providing evidence for the general theory of relativity. And from there on, Einstein obviously was able to go forth and make more progress as well. But this was a huge step forward. Today, we've reproduced this many times over. Just recently, in recent years, I know of some astronomers who did this back in 2017. It's a fascinating exercise to see the stars shift their position because of the sun's gravity. Well, there's other more extreme cases of gravitational lensing. Look at the top 2 pictures. Here we see in the center a small dot of light. That's a dense, massive gravity of a galaxy. Okay. On the left, you see 4 dots surrounding, and on the right, you see a ring of light. Those are not physical objects. That is the distorted, bent light of galaxies behind the central galaxy. No surprise, they call the one on the left an Einstein cross, the one on the right an Einstein ring. But the light from galaxies behind the foreground galaxy is bent in such a way that we see either multiple images or sometimes even a ring. Look in the bottom here. I'm going to play this little animation for you, showing you what this would look like if you could watch over time an object of great mass moving in front of distant galaxies. That's what you'd see. And we have pictures like this. I didn't include one here today. But notice you don't even see the object, but you notice the effect of its gravity. That could very much be like a black hole moving in front of the light from these distant objects. Once again, this is a clear effect of general relativity, the bending of starlight in a gravitational lens. Without that theory, we cannot explain this. So you can see why it's very important in astronomy. Kind of neat to see that, isn't that? That would take some time to see it move, but it's a nice animation to help us visualize that. Well, let's go back then to gravitational waves. I'll make a few more comments here. 2015 was the year when we first detected gravitational waves using that LIGO observatory I mentioned. Got to tell you, there was a tremendous amount of time, effort, and money to make this happen. This project goes back 20 years. It was funded by the National Science Foundation, and it took enormous, again, time, energy, and effort, but here's the result. You see some funny squiggly lines at the top right there? Those are the actual signals of gravitational waves. And below that, you see a visual animation of that. What's going on here? Well, as I mentioned before, we predicted that if two very massive objects, in this case, two black holes orbiting each other, were to finally crash together, there would be enormous amount of energy changed into gravitational waves. It says that 3 solar masses were converted into gravitational waves. How much is that? Well, sounds like a lot, right? Well, let me put it to you this way. When we detonate a nuclear device, you probably know those devices have several kilograms of nuclear fuel, right? Several kilograms. The sun has approximately 10 to the 30th kilograms. So imagine 3 times 10 to the 30th kilograms of matter changing into energy. It's inconceivable. You can see a different way to look at that. 10 to the 49th watts. I was tempted to write out 49 zeros, but I think you get the point, okay? This is an unimaginable amount of energy. When this occurs, changed into gravitational waves. The only reason you and I didn't notice it is because it was so far away, hundreds of millions of light years away. These events were detecting, requiring a very, very sensitive detector. In the bottom right is a nice chart. This was put together by a friend of mine, Aaron Geller at Northwestern University, showing some of the more recent detections of gravitational waves. And what's interesting here, obviously, with any science, as you begin to get more examples, you begin to get a better insight, don't you? You get a better picture of what's going on. You don't just see 1 or 2 individual events. Notice our range of masses of objects, starting at the bottom, down at 1 and 2 times the mass of the sun, moving up to the top over 100. This is telling us that objects of varying masses undergo these mergers. The very bottom, low mass objects called neutron stars, and then as you move your way up, black holes clearly. So we're now able to get more understanding of black holes by studying gravitational waves. Isn't that interesting how these became complementary fields? And we've made some amazing discoveries. Sure, there were a few of these events we expected, but there have been some that we did not expect. And so again, you can see how science progresses here. It is not an exaggeration to say that this is an entirely new way to see the universe. We've always used light, haven't we? And we'll continue to do that. Humans have always used light to see the universe. Now we can, in effect, so to speak, see gravity waves. And that's another whole topic. As I've said before, I have another whole lecture on that if you want to go out to YouTube and watch that lecture. Well, one final piece I'll add here, I just thought it was a very noteworthy example, again, in astronomy of gravitational waves. 2 of the lower mass objects observed back in 2017 merging were 2 neutron stars. What was unique about this event was we not only detected the gravitational waves, but through an intense international collaboration, astronomers also saw light of all these different wavelengths you see here, X-ray, ultraviolet, infrared, from this event. So this is huge, to be able to not only see the gravitational waves or see the light, but to see them from the same event. In fact, there was such intense collaboration, many have said this is probably the most intensely observed astronomical event ever done. Many, many dozens of teams of dozens and dozens of astronomers participated in this. This was called now a kilonova. And already there was a significant, I think it's fair to call it a discovery. Before this event, we had a pretty good idea of how heavy elements in the universe are made. Things like carbon, oxygen, neon, iron. Well, there were a few elements we were having a little trouble explaining their origin, But when this event was detected and scientists went back, they determined that this could be where some of those elements are created, such as the gold in your jewelry. Wouldn't that be an interesting thought? Who knows? Maybe somewhere, sometime in the ancient past, some of that material was spread through our solar system and ended up on Earth. All those heavy elements, of course, are important. That's what our Earth is made out of, right? And you and I, we're made out of carbon and oxygen and different elements. So it is pretty neat to think about, how these very extreme events and occurrences out in distant space actually do have a little bit to do with our existence here on our tiny little planet, precious as it is. Well, let me just finish up with a few comments here on the benefits of relativity. And first and foremost, you can see the first one. I think I mentioned this at the outset. We simply need to know, don't we? Humans have always been curious about the natural world, about the universe. That's never going to change. And so much has come from that. When you think about what we've learned over the thousands of years, think of the deeper insight, especially since, again, we developed the methods of science to give us a very rigorous, a very, logical way of learning about the universe. I'm just going to hit on a couple things here. Electricity and magnetism. 200 years ago, those were no more than a curiosity. There's the story, of course, I think of Benjamin Franklin flying his kite, right, and got zapped by lightning. People thought, oh, electricity, what is that? That's kind of, think about the role of electricity in our modern world. And I don't just mean electric lights, electric motors, those kind of things. But as I'll get to in a minute, our technology. How far we've come, even in the last 50 to 100 years. I could talk for hours about this, couldn't we? How about light? Back in the 19th century, scientists thought they were learning about light, and they do experiments, and they'd say, oh, light's a particle. And then they do another experiment, say, no, light's a wave. Who was right? Actually, they both were right. You might know that light has the properties of a particle, and it has the properties of a wave. I sometimes tell my students that's not so strange as it might seem. Even people can be more than one thing, right? You might be a student in my class. You might be an employee at a building. You might be a parent. You might be a relative. There's any number of roles you might fill. Well, it's not too much of a stretch to just say light has properties of both. We can do simple experiments to prove that it's a particle and a wave. That has led to so many amazing insights into our universe. Nuclear fusion, again, based on Einstein's equation, explains to us how the sun shines. Black holes, we never dreamed of black holes centuries ago, that there could be such things. So where has it all led? Again, I could spend hours talking about the benefits. You can see a couple of things here. Let's go back to electricity. You go back 200 years, people would not even be able to imagine a radio. Then we developed television, computers, satellites put into space so we can talk to each other on any location on this planet if we want. And my goodness, the internet in the last 25 years. What can we say about that? How that has changed humanity. I like to always joke that these days we talk to our computers, don't we? We talk to our GPS. Tell me how to go here, tell me how to go there. Our computers can understand us. So how far has science brought us? Well, I think you can see the fundamental importance of something like the theory of relativity and why. Scientists pursue these theories, develop them, refine them, improve them, so that we understand the natural world better. Number one, for our curiosity. Number two, to gain deeper insights. But number three, even for practical benefits. I think you can see how important science can be. Well, in conclusion, I'll just make a couple of comments. I think Einstein was right. Don't you think so? The theory of relativity is a fundamentally profound discovery. It really is the foundation of all our modern physics. It is the accepted theory of the universe. It continues to be tested. Just recently, there were or more tests performed, it has always passed tests. And so it's safe to say it provides our best understanding of the universe. And so I think you can see its importance. I was able to touch on a few examples of it here in astronomy, but in so many other fields as well. So I'll just leave you with this thought from Werner Heisenberg. Maybe you feel like he did. He said, the universe is not only stranger than we think, it is sometimes stranger than we can think. So I hope you've enjoyed our little discussion on relativity tonight. Thank you for being with us. At this time, we will pause. And before I turn it back over to Julie, as I've already mentioned a couple of times, just want to remind you, if you enjoyed the talk, there's plenty more of those out on YouTube. You can see a number of the topics there, black holes I mentioned, Spitzer Space Telescope, extrasolar planets. And if you, again, have never had the chance to maybe take a course in astronomy, here's some small courses you can do so at your own convenience. These are 20, 25-minute lectures on a variety of topics, but they all build together into a short course on both the solar system and stars and galaxies. So thank you again for joining us tonight. At this point, I will turn it back to Julie, and we'll get ready to take a few questions.
Our first question that we have here tonight, let's see. So if I understand gravitational time dilation correctly, would that mean that time goes faster the further away a person gets from the surface of the massive Earth, even though it's not noticed by human senses? An example would be, would time be faster on the observation deck of the Empire State Building than in the library, in the lobby?
That's an interesting question, and the answer is yes. Even though, of course, mathematically would be a very, very, very small effect. The farther you are from the center of the Earth, the difference gradually grows. It's probably better to think of it as if you were floating out in deep space somewhere away from any gravity, you would measure time a certain way. And as you approached any object, whether it's the Earth or some other massive object, then the time would slow slightly. And that does not mean there is an absolute universal time deep out in space. All I'm saying is in the absence of gravity, you'd have a certain rate. And then you'd notice it as you get closer to the object. Indulge me 1 second. Many of you have probably seen the movie Interstellar, and they are going to go explore this black hole. Two of the crew get in the ship. They go down to this planet closer to the black hole, and they touch on this. They know they got to hurry up because they know that time is traveling slower for them. When they get back to the ship, isn't that a dramatic moment if you've seen that? They come back to their comrade and they say, oh, how long were we gone? And he says, you were gone like 20 years. So it's a dramatic dramatization, but it is true. Yeah, the farther you are away from the gravity, then the difference would grow. Okay, thanks for that.
Yeah, so Joe, I'm sending you a couple of questions in from the chat. One of them that came in is, how do we know that gravity waves are produced by neutron stars or black holes?
That's a complicated one. I have another good friend at Northwestern that is part of that team that works at LIGO. I wish he were here to answer that one, but essentially it has to do again with the relativistic effect on the curvature of space-time. As these objects are orbiting each other, they're both, of course, curving space-time, aren't they? And the closer and closer they get together, the stronger the effect becomes. To me, that would be just a simple way to describe it. Of course, when they merge together and there's this tremendous release of energy, then you get the strongest gravitational wave of all. But I think that might be a simple way to kind of view that they each have a curvature of space, and as they get closer and closer, the effect strengthens. There's one here about what would it feel like if gravitational waves got closer to Earth or originated. That's a good way to say that. Would it feel like waves at the beach? It wouldn't be really pleasant, I got to tell you. Because remember, what we're talking about is space itself expanding and contracting. That means not only our planet would expand and contract, your body would expand and contract, and that might not be so comfortable. I haven't read too much about that in specific, but we really don't want that too close to Earth, and we don't think it's going to happen. These are very, very, very weak effects unless you have very, very close to the object. So at this point, we needn't worry, but it would be an interesting experience, I guess, if you were to notice that. Okay. Let's see. Energy derives from mass, but why is the factor c squared in Einstein's equation? that's a mathematical derivation. That's a mathematical derivation to go back and go through Einstein's equations to find that c squared. It really, again, is telling us that the factor is a large factor, a large amount of energy stored in a very small amount of mass. That's why our nuclear weapons are so powerful and the sun is so powerful. You could also think of it as the fact that there is this relationship between the speed of light and so many things actually we find. We find in the theory that the speed of light c keeps kind of popping up. And so that's partially, I can't get inside Einstein's mind, but that's partially why he realized it was so important. Essentially what he said was the speed of light is one of the very few things in relativity that is fixed. Everything else must change. You saw how time changes. You saw how distance changes. You saw how mass changes. Those things that you and me would never have thought could change. But Einstein said the speed of light never changes. Everything else must change to basically accommodate that. So very interesting way to look at the theory, how the speed of light is just so central to really both parts of the theory. All right, let's take a look down. The chirp. Yeah, so a few of you have made some comments, which tells me you have learned a little bit about the gravitational waves. That's what it's called. And that's a good point. I think Bob has made a comment. The signature of the chirp allows them to find the size of it. That's a very good point. Thank you, Bob. That's exactly right. It is a fairly complex, analysis to be able to determine that, and it takes a significant team to be able to do that. There's one other question here, a little bit off topic, but Heisenberg's uncertainty principle. During the early to mid 20th century, of course, Einstein developed his theory, and it was tested, and we learned a great deal. You might also know there was another theory at the time, quantum mechanics, that was developed regarding the very, very, very small realm of the atom, and especially smaller. And interestingly, that whole theory does bring with it, as was mentioned here by Greg, some uncertainty. Einstein was never really comfortable with that. He just kind of had this gut feeling that there shouldn't be this inability to know something precisely as much as we wanted. So that's an interesting off topic to go off and look at, that uncertainty principle. He made this famous comment. I think it was obviously metaphorical, but this inherent uncertainty in the natural world. He didn't like that. He said, God does not play dice. In other words, God doesn't do things by chance. I thought that was an interesting comment he made. And I thought somewhere, yeah, thank you, Bob, also for Shane Larson's presentation. Shane is the other astronomer that I mentioned at Northwestern. Great guy, full of energy, and I love Shane, and he does a great job. He has that exciting opportunity to be part of the LIGO team. I thought that was really great. I got to catch up with him. Well, Matthew's got a question. If you were to survive the conditions of space on the event horizon of a black hole where time stops, would the stopping of time affect you? Doesn't sound very pleasant, does it? Here's what's neat about that. You have to remember that when we talk about the difference in how time flows in a gravitational field, that is from the perspective of an outside observer. In other words, if I'm floating back 1 million miles away from the black hole and I watch you fall towards the black hole, I'm going to see your time slow down, as I mentioned during the lecture, slower and slower and slower. But to you, you're not going to notice anything. You're going to feel like time is time. It's my time. You're going to fall into that black hole. So that's what's, again, kind of unique about time dilation, is that the two observers have a very different experience. And again, they kind of made a nice dramatization, I thought, in the movie of that. So the two that went down to the surface, they didn't think anything differently. They said, we're 3 hours older than we were when we left, but the astronaut above was 20 years older. So that's the difference there. You're still going to fall in. Sorry, you can't get away. Okay. But to an outside observer, they would see that change. Okay. So good question. And that was interesting. Okay. Anything else? I think I got you thinking. And that's what relativity does. It takes a little time to kind of, I sometimes say, internalize that and get comfortable. But I will tell you this, the longer you kind of learn about this and think about it, and it becomes a little more familiar, it really opens up a fascinating view of our universe. It really does. I have made some progress along those lines. I look at things differently. There is no absolute time. There is no absolute this or that. That doesn't make the universe less interesting or more confusing. It makes it more interesting. And frankly, in some ways, kind of more beautiful. Think about what a just amazing universe we live in, how these laws that we have now improved our understanding than we had, again, 100, 150 years ago. So try to look at it that way. If it feels a little uncomfortable, that's okay. I tell my students it takes a little time. And yet, once you begin to kind of accept that, it feels better. And it's a much more fascinating universe than it used to be.
Joe, I do have a question.
Sure.
For those that are interested in learning more, do you have any book recommendations or resources for where they can find out more on this topic?
Well, these days, of course, there is just so much information available. I have a few books in my personal library that I've read that have, again, helped me grasp and internalize this kind of thing. I don't have one here at my fingertips. There's obviously lots and lots of websites. I will tell you, as I've looked at a number of websites, most are quite good and quite accurate. Sometimes you'll run into one that where the way it's described can be a little difficult to grasp, because it is true that it's hard to keep your language just rigorously precise. Sometimes you might, I've done it where I've said it just a little bit of the wrong way. So I can't think of anything off the top of my head. I will tell you, Einstein way back wrote a very short work of his own that I thought was excellent. It was very clear. I didn't know he could write until I read this years ago, and I thought that's really quite good. It was very basic, simple algebra, gave you a little bit deeper view than just the conceptual pieces here. So not one in particular jumps out at me. There are some obviously going to be much more rigorous. If any of you have mathematics and the training for that, that gives you an even deeper understanding of how it all works. But if you really want one, send me an email and I'll dig through my library and make a recommendation. All right, anything else we got here? Let's just take one more look here. Jacob's got one. If an object's mass increases as its velocity gets closer to the speed of light, would we observe the object getting bigger, smaller, depending on its velocity? That's a good question. And the short answer is no. We're not going to notice its size changing that much, but we would notice all of those effects. And I hate to say simultaneously, but in other words, number one, the mass increases. What that means is, let's say that you had a rocket and you were somehow able to magically fire its engine for, a year without running out of fuel. I know that's pretty impractical, but when the rocket begins, of course, it's going to begin to accelerate at a certain rate, maybe every 10 meters per second. That's just a number that we use sometimes for gravity here on Earth. But the faster and faster and faster and faster it goes, we begin to see the acceleration decrease, as we talked about. Why? Because the mass is increasing, even if the rocket provided a constant thrust. What else would we see as it goes faster and faster and faster? We'd see its length begin to change. We would not be able to determine the exact same simultaneity of events that might be happening on board that ship if there was some way for them to communicate with us. So all of the effects kind of kick in together, okay? Again, the length in the direction of travel would appear to us to begin to change, but the object itself would not necessarily appear bigger or smaller, if I understood your question. Okay, so thank you for that. All right, any more? We got time for maybe one more if anybody's got one. But I hope I've given you lots to think about, stretch our minds a little bit. I always enjoy relativity because it is such a fascinating topic. And again, gives you a very different view of the universe, doesn't it? It always reminds me how much there always is to learn. I touched just briefly on the fact that during the mid-19th centuries, scientists were getting a little bit, I won't say smug, but we felt we had things pretty much figured out. There were a few more details to learn about, but everybody felt like Newton's laws explained everything. And as you saw, there were a few mysteries that said, well, wait a minute, we need to look at this again, think about this a little differently. And that led to this theory. So who knows where we will go in the future? Right now, we have an outstanding theory. It's been tested dozens of times. We're extremely confident in it. Where will it lead us? I'll maybe just finish with this comment. I see one more question there. I mentioned earlier this other theory of quantum mechanics, the theory of the very, very, very small. The big challenge today for science in general is to somehow get these two theories, to work together. In other words, relativity explains the very, very large. Quantum mechanics explains the very, very small, but mathematically especially, they don't work so well together. So scientists have been working very hard and are continuing to work very hard on trying to somehow harmonize these two. That's the big one. And if we're able to do that, we feel there will be a huge jump in our understanding, a huge increase, a huge improvement in our understanding of the universe. If we can somehow take these two theories and merge them. Einstein gave it a shot before he died, couldn't do it. Others have tried for years and have made some progress, but just can't quite get the two to work fully together. If and when that's able to happen, we are going to feel like we really do have another whole big giant leap forward in our knowledge. Okay. Oh, does the mass of galaxies increase as space expands? Well, that question might have to do with the fact that, again, the universe is expanding, space is expanding. And it's an interesting question. You would think, well, the galaxies are going faster and faster and faster, right? Is their mass increasing? No. Here's why. Einstein's theory, the equations, the effect, deal with motion through space. You travel through space, you accelerate through space. But if space is carrying you, that sort of doesn't count. So the galaxy's masses are not increasing. Otherwise, we'd have this incredibly powerful effect. Because frankly, some galaxies are receding from us at almost the speed of light. Isn't that amazing to think about it? So interesting question, but in this case, there's a little exception, if you will. Okay. All right. Well, if there's no other questions, again, I'll say thank you to everyone for joining us tonight. I hope to see you again, whether here or in person. But thank you for being with us tonight and have a nice evening.